Hey guys, we are continuing the topic of complex numbers. We just looked at complex numbers, the basics. We looked at what a complex number is, and I explained why the word complex doesn't actually mean complicated, complex in a complicated sense, but complex in a compound sense. And we looked at adding and subtracting and multiplying, although we've not looked at dividing. So if there is enough time in this video, I'll just quickly brush up that division aspect. So we want to basically start from the graphical representation of a complex number, because if we look at the graphical representation and we understand it, we'll be able to express complex numbers in polar form. All right, so let's start with the graphical representation. We know that on our Cartesian plane of real numbers, um, we have a plane that looks like this. It's a two-dimensional plane, and we have a set of integers, zero in the middle. We have the positive numbers going on one side, and we have the negative numbers going on another side. Exactly. So if we take 3 for example, and we multiply 3 by minus 1, we multiply 3 by minus 1. This is 3 here. I want to graph this. These are two real numbers. 3 is a real number, which is equal to plus 3. And if we multiply 3 by minus 1, we get minus 3, which is a real number, but it's negative. So this is where 3 is going to be located on our Cartesian plane. 3 will be here. And what about minus 3? Minus 3 is going to be here on the other side. This is what we know. Minus 3 is going to be here. So now, I want us to take note of something. Remember, we are trying to graph complex numbers, not just real numbers now. But I want to introduce the idea from what we already know from our junior secondary school. In fact, the multiplying minus 1 to 3, or multiplying 3 by minus 1, has the effect of rotating 180 degrees. Remember, angle on a straight line is 180 degrees. So 180 degrees rotation is what we did here. That's to go from 3 to minus 1. So, and in fact, the way I drew my arrow is very key. Don't forget, it should not be drawn the other way around. So this is counterclockwise. I will just write it. I drew my arrow in a counterclockwise manner. So in fact, angles, when we are dealing with complex numbers, just like when we are dealing with trigonometry, are taken counterclockwise, not clockwise. Good. That is positive angles. If you take it clockwise, you are now taking negative angle calculations. So now, remember from the previous class or the previous lecture that this minus 1 in itself is actually it's a product of a complex of a complex number, the imaginary part. Remember that. Let me just write it just as a recap. Remember we said that I is equal to the root of minus 1. Exactly. Therefore, when you multiply I times I to give you I squared, you are now getting the root of minus 1 squared, which is equal to minus 1. Exactly. All right. So if you compare this with what we have here, it means that this minus 1 can be taken as this, since I times I is what is giving us minus 1 here. Good. So if multiplying by a negative if multiplying by minus 1 is giving us a rotation of 180 degree, what rotation will multiplying by I give us? So let me explain it this way. Um, we already have, I'm going to redraw a Cartesian plane, and I will draw it in terms of two different axes now. two different axes, and I have my reason for that. And this horizontal axis, which if this is my origin, I'll call this x. Good. We know, of course, that the horizontal axis, which is OX, is representing the real part of Z. Is representing the real part of Z. I hope we are clear with my explanation. Remember the real numbers, the real part of Z. Good. Now, what we are finding, what we really want to do or know is the imaginary part, because that's what makes the number actually complex. Good. And we said from here that if you multiply 3, this is 3, somewhere here, if we multiply 3 by I plus I, by I two times, we have the effect of rotating by 180 degrees, which is in the counterclockwise manner. It looks like this. So from here, we landed at this point. So definitely, if multiplying twice by I has the effect of 180-degree rotation, multiplying once by I alone, let's leave what the I and the I mean for now, and let's focus on their imaginary notations in itself, so that we won't get confused. Multiply by I two times has the effect of 180 degrees. It means that the effect that multiplying by only I will have will be effect of half 180 degrees, which is 90 degrees. So if two of something results in 180, one of that thing will result in 90. And we know that from here, if you measure 90 degrees in the counterclockwise manner, you end up at this point. It means that you are going to have your 3I somewhere here. That's 3 times I now is going to be somewhere here. 3I. So I hope that makes sense. It's a conceptual something, but if you calm down and you reason it very well, you'll see that it makes sense. So now, if we take this a little step further and say we have our 3I here, and let's assume, because we can also have imaginary numbers that are negative, imaginary numbers that are positive. So if we multiply 3I by minus 1 again, we know already that minus 1 is the product of I times I. So if it will help you to understand this if you have looked at my previous video where we looked at powers of complex numbers. But I wrote it here. This one is not so difficult. The product of I by itself, that's in two places. Let me put it in two places, will give us minus 1. So anytime you see minus 1, when you're trying to understand this graphical representation, just know that it is I in two places. So, and we said it has the effect of rotating 180 degrees. So I have my 3I here and I multiply by I in two places, which is by minus 1. The effect will be that I will rotate from here 180 degrees to this point. So my minus 3I is going to be somewhere here. So when we look at this, if I call this Y, you see that my axis OY, remember we said OX is the horizontal axis, and OY will be the vertical axis. Axis OY will be representing the imaginary parts of Z. The imaginary parts of Z. And as you can see, you have your I values, your I parts on your OY, your vertical axis, and you have the part without the I, that is a simple part, let me put it that way, on the horizontal axis or the OX axis. This diagram, we call it the Argand diagram. At times, if you know names of something, you would understand it better. It's called the Argand diagram. So if you want to define it, it's just simply a diagram that graphically represents a complex number where the horizontal axis, which is OX, represents the real part of that complex number, and the vertical axis or the OY axis represents the imaginary part of that complex number. That is what an Argand diagram is, and it is different from a Cartesian plane. It's not a Cartesian plane. So take note of that. All right. So let us say I want to graph I want to graph, wish to graph 3 plus 5i on an Argand diagram. Or let me just say an Argand plane. So how would this look like? Now this is not to scale, but we know that it's going to look somewhat like this. We know that the 3 is the real part. Let me just write it for the sake of writing. And what's our imaginary part? Now our imaginary part, I am of z, exactly. 3 is real. Our imaginary part is 5. But remember I said that in the previous video that it's somewhat like a confusion, because 5 is actually like a real part. So if you don't understand it conceptually, you might just get rid of I and you will just stop writing I. But always know that conceptually 5i is the imaginary part, or conceptually I is the imaginary part, if not 5i. So but 5 is a bit can lead to a misunderstanding if we are not careful. So remember that the real part, from what we've established just previously, we said the real part is graphed on the horizontal axis, which is the OX axis, this part. So let's say, not to scale, but let's say our 3 is here. Let's just say our 3 is here. And okay, let's say 1, 2, 3, 4, 5. Let's put it that way. And on this side we have 1, 2, 3, 4, 5. So like I said, not to scale, so please don't sue me. So the imaginary part is, this is the I-axis. So I can even write I here, and that I am of z, so that we'll know. And here I'll write RE of z, so something like that. So exactly. So our 5i is going to be somewhere here. If we count, I don't know how to scale, so there's no point. So our 5 is going to be here. Our 5i is going to be here. So it's similar to the way we graph on the Cartesian plane. We graph a two-dimensional equation on the Cartesian plane. When I say two-dimensional, I mean two variable, like an equation having x and y. So we usually keep the x on one side, the y on the vertical axis, and the x on the horizontal axis. But in this case, it's not Cartesian plane, it's an Argand diagram, but we use the same pattern. So where will our complex number be? This complex number, 3 plus 5i, we're going to look for where these two axes intersect. So just using your broken line and your ruler, you can see that the two axes intersect at this point. So I'm just going to mark that point, and I'm going to write my z there. So this point is where our complex number is located on this Argand diagram. Exactly this point. So take note, a complex number is not a line, no, it's a point. It's a point, and that is the point which I have marked here, z. So I hope this is not it's not so confusing. Okay, let me just go one step further. If it were to be -5, if z was to be -5 minus 5i, and we were to graph this, we know of course that our -3 will be somewhere here, not to scale, -3, and our -5i will be somewhere here, -5i. So if we were to look for where these two axes intersect using our broken line, that's what we most commonly do, and it makes sense to avoid errors. We see that they intersect at some point here. When you use a ruler, you will get the accurate value, and this point is what we'll call our z. So this, like I said, don't forget that the complex number is just the points on the Argand diagram, and this is the point which we have marked. Good. So if we want to express this number now, let us start with the first one in polar form. Now, a polar form is, in polar form now, we're going to draw a line. So we have something like this. I drew one side, I drew the positive axis of our Argand diagram. I drew the positive axis of our Argand diagram. So this is I. This is plus Im of z. You know why I'm writing plus now. And this is plus Re of z. So I'm writing plus here because, of course, the negative side will be on this other side, and the negative side will be facing downwards. So if, let's say, we have a complex number at some point here, Good. And that is Z. I'll just write it there, Z. This is the origin O. Good. Polar form requires number one that you draw a line from your origin to the complex number, so that your complex number is now a vector, because a vector, if you remember, a vector has a magnitude, magnitude and direction. Exactly, a vector has a magnitude and direction. So a complex number, the complex number, when you draw a line, is now a vector, because the distance, or the length of this line that you drew is the magnitude, the magnitudinal part. And where the arrow is facing, which we can express with an angle drawn from our positive x-axis to where the vector is, theta, is going to be our direction. So remember, the complex number in itself, you got it when you join the real part and the imaginary part. You use your ruler to check the intersection where the two axes joined or intersected on the Argand diagram. So the real part is represented by A, don't forget from the previous video, and the imaginary part is represented by B. So I'll just put B here, or you can put B, BI, or BJ, whatever. So this is the understanding of polar form. If you look at it carefully now, the distance or the length of the line, the magnitude, we use R to represent it. It's a convention. You can use any letter, it doesn't make any difference. But R is the convention. So in order to get R here, you can see definitely we use Pythagoras theorem. We get a rectangle here. Once this broken line completes the shape to get a rectangle, meaning if from here to here is B, this is also B, and this is also A. Just put something like this to make it easier to understand. Good. So it means if we have two right angle triangle, and if you consider one part of this triangle, we can say that from Pythagoras theorem, let me write it out. Pythagoras theorem, r squared is equal to a squared plus b squared, and therefore our r is equal to the square root of a squared plus b squared, as you can see here. Exactly. So then what is A and what is B? That is another thing we should take note of. So once we find our R, we can find A and we can find B. Our theta here, or we can say theta, if we take the sines and the cosines of theta, we can get our A and our B. For example, sine theta is opposite of our hypotenuse, and looking at our angle from here, our opposite is B and our hypotenuse is the R itself, so B over R. And cos theta is adjacent of our hypotenuse, and this is our adjacent side. If you look at it, while this is the opposite side, cos theta is A over R. So I'm just showing you how to this. If you've done vectors, actually this will not be confusing for you. It won't be confusing for you. So we have expressed B and A as sines and cosines of theta. I can say my B is equal to R sine theta when I cross multiply, and my A is equal to R cos theta. So just something like this. So if let's say we have A and B and we are looking for theta, we can also say that tan theta is, remember what tan theta is opposite over adjacent, which is B over A. Let's assume we have B over A and we are looking for what the angle is. Tan theta is equal to B over A. So these are different equations that we should take note of. So, but remember that a complex number, the general form of a complex number is A plus what? A plus BI. But now that we've said our A is given as R cos theta, we can now see that complex number in polar form now will be r cos theta plus our b is what, r sin theta plus r sin theta I or j, whatever. Since r is common, we say our z is equal to r into cos theta plus sin plus sin theta I sin theta. So you can put it at the back and the front, anyone, it doesn't make any difference. So if we say, let us just to round up the class, 3 plus 5i, if we want to express 3 plus 5i in polar form, just I will use this example to round up the class. Express 3 plus 5i in polar form. So what do we do? We know that in polar form, z is equal to r cos theta plus sin theta I, or is it I sin theta? So the real part is our cos theta, and the imaginary part is our sin theta, is having the sin theta. So commit that to memory. All right. So we just need to find our r, and remember our r, we use Pythagoras theorem. This is a, this is b, don't forget. So our r squared, to get the r, our r squared is equal to 3 squared, which is a squared plus b squared. Remember, these are two sides of our triangle, which is the horizontal side and the vertical side. Then the arrow is the hypotenuse, which is the vector itself, and we're looking for the magnitude of that vector. So 3 squared plus 5 squared, will give us 9 plus 25, which is equal to 30 what? 34. So therefore r is equal to the square root of 34. The square root of 34. Then what about theta? In order to get theta, I believe you know what to do. We just say what? We just say tan theta. Remember, we had all those formulas here. So, but if you forget the formulas, you have to draw this diagram and understand what I explained here. Then it will not be a big deal for you. So if you understand, if you have any question, you can drop it in the comment section. But it's actually not a hard concept at all. Tan theta is opposite. So what is the opposite? Now we know where the angle is. Our opposite is going to be, remember, you picture something like this. Once you picture something like this, you imagine that you have your angle here, and this is your opposite. And this opposite is vertical, meaning it's the B part, and you have your adjacent here, and your adjacent is the A part because it's horizontal. It's the OX axis. So B over A, which is going to be 5 over 3. And once you say your theta is equal to the tan inverse of 5 over 3, and you get your answer. So once you simplify this, I don't have my calculator with me, so I would have simplified this. Once you simplify this, you're good to go. You just write it in this form. Once you write it in this form, you're good to go. So I'm going to create another video solving more questions, expressing more complex numbers in polar form. But for now, I'm going to stop here, and the division, I'm going to push it to the later video as well. But if you have any question, please you can drop it in the comment box, you can email me, or you can call my number. And please like this video, share this video. If you know anybody that is having it difficult with complex number, you can share the video to them. So, but one last thing we should know is that the r here is called the modulus. Where do I write that? All right, we said we have, this is the polar form. R here is called the modulus. And the theta here that we'll be looking for, that we use the tangent function to find just now, is called the argument. So when you see the word argument in complex number, they're referring to that angle itself. So they have their funny analogies. In vectors, there's nothing like argument, but in complex number, we call it argument. So thank you for watching, guys.